Alright, so I'm going to walk you guys through the solutions to the worksheet we were doing in class on thermodynamics. The first few that are pretty straightforward, I'll just be giving you sort of a general idea of a solution to. The other ones I'll go into a little bit more detail. Anyway, here we go. Number one, oops, gotta get into my pens here. Let's go for it. Number one. How many calories would it take to heat 4.3 kilograms of water from 278 Kelvin to 304 Kelvin? Well, since we're dealing with water, we know that the specific heat is 1 calorie per gram per Kelvin, and that change in temperature, let's see, it gives us 27 kelvins. Okay, so plugging those numbers into Q equals mc delta T will give you the correct answer. Number two, how many calories would it take to melt 3.4 kilograms of ice? And it says at 273 Kelvin. So that's suggesting that the ice is already at the melting point. All we have to do is melt it. So MHF, mass 3.4 kilograms, which we of course have to convert to 3,400 grams. And I should mention, we should do the same thing up here to 4,300 grams. All right, so, and then heat of fusion for water is, let's see what we're using here, calories or, yeah, calories, so 80 calories per gram. Plug those two things and you'll get, again, the desired answer. Number three, how many joules would it take to completely boil 150 kilograms of water? Well, that's a lot of water. So 150 kilograms is in the neighborhood of 320 pounds of water. That's a significant amount of water. So you expect this to be a pretty high number. For boiling, we're dealing with MHV. Okay, mass is that given 150 kilograms. NHV number you could look up. We're doing joules this time, so it's 2,250 joules per gram. Okay, of course this would be 150,000 grams. Okay, always be careful with the units. Make sure that they all agree before you start just plugging things into a calculator. Number four, how many BTUs would it take to begin with 10 pounds of ice at 0 degrees Celsius and get it to steam? Okay, so we got to heat it, get it from ice, melt it, heat it up, boil it. Well, if we take a look at the graph we're supposed to use every time. Okay, this guy. Our starting point in this case is right down here. Okay, so we're at the melting point, but we're on the solid side of it to the left here. And then we melt, heat up, boil, and end there. So there's going to be 1, 2, 3 steps to this number 4. So the first thing we have to do is MHF to melt it. Second will be MC delta T to get it from 0 degrees up to 100 degrees Celsius. And then lastly would be MHV. Okay, for the boiling process. Now, the tricky part of this problem is that the numbers are given to you in terms of BTUs and pounds, but also then Celsius. Well, those units those don't play well together, so we've got to change one of them. Well, the BTUs, joules, or calories is not nice. So instead, conveniently, the temperatures that we're dealing with, 0 degrees Celsius, well, we know that's the melting point of water, which we know is 32 degrees Fahrenheit. and the higher temperature is 100 degrees Celsius. The boiling point of water, which we should know by now, is 212 degrees Fahrenheit, giving us, if we subtract those two numbers, a change in temperature of 180 degrees Fahrenheit. Okay, so heat of fusion, I gave you in class in BTUs, was I believe 144. Heat of vaporization was somewhere around 967. Okay, so let me just in red, I guess, underline the numbers you'll need for. Okay, so numbers you'll need to plug in are these guys. Keep going away. There we go. All right, and then the mass, of course, was 10 pounds. And since BTUs and degrees Fahrenheit are okay with using pounds, we're all set to go ahead and plug those in. We would take these three numbers and add them together to get our final answer. Number 5, if you added 100,000 joules, okay, this one's a bit of a twist where we know the change in heat energy, but we don't know necessarily the result of that. Okay, what would the temperature change of the glass be? Okay, assuming no phase change. Well, assuming no phase change, we're simply dealing with Q equals mc delta T and solving for delta G this time. Okay, not too difficult, so I won't go too much further into it. We'll just keep plugging along. Number 6, how many kilograms of mercury would increase by 100 Kelvin when a certain amount of heat energy? Well, again, we're not dealing with a phase change, so it's just mc delta T. And the hitch in this one is, well, we know the heat energy and we know the change in temperature, and we're given the specific heat. And this time we are solving for the mass. Okay, pretty much the same type of thing as number 5, but just sort of an exercise in the flexibility of this kind of equation. All right, so moving down a little bit further, a little too far. Number 7, this is where the problems got a little bit tricky. Will the final equilibrium temperature of the mixture be? Well, we've got 2.1 kilograms of water at 5 degrees Celsius and 3 kilograms of water at 39 degrees Celsius. Okay. Well, we're dealing with water and water here, so the specific heats are the same. And it doesn't particularly matter which units we use, so I'm just going to use calories. That's convenient because it's 1. The specific heats are the same, so the determining factor in where this equilibrium temperature is going to be is the mass. Okay, so the mass of the hotter one is 3 kilograms. Okay, that holds more heat energy than the 2.1 kilograms will. Therefore, the temperature, which we know is going to be in between these two, is going to be on the side of the 39. And I believe, well, let's go through at least the setup. Okay, with any mixture problem, we are setting up delta Q equals delta Q. So, again, conveniently, since there's no phase change, okay, we're just dealing with mc delta T. We've dealt with some more complicated problems in class, or we will shortly if we haven't already. Okay, so mass of the, let's say A, call it A, so I'll call this guy A, this guy B. So mass of A, specific heat of A, times temperature final minus temperature A. And then I'll do the same thing over here with B on all of those things. And again, recall that since we're dealing with a mixture here and we're trying to find this equilibrium temperature, this TF, okay, those two TFs will be the same number. That's what the equilibrium temperature means. Okay, and when you solve this out, I believe you get a final temperature of about 25.1 degrees Celsius. Okay. Number 8, took it a short step further, and now we're combining some water, 10 kilograms H2O at 12 degrees Celsius, and we're going to take a piece of iron, red hot or something like that. Okay, 5 kilograms at 90 degrees Celsius. Okay. So the setup is really the same here. We just end up plugging in different numbers. So if delta Q equals minus delta Q, okay, MC delta T equals minus MC delta T. So I have, I guess I'll call this A and this B this time, or the iron and water. Mass of A, the water, specific heat of A, the water, TF minus 12 equals mass of B, the iron, specific heat of B, minus 90 this time. Okay, and for this one, if we consider, we know that it's going to be between 90 and 12. Okay, it has to be, just physically, logically it has to be. And there's two factors that will play into where it falls in that range. One is the specific heats of the two materials. Here we're not dealing with water and water, we're dealing with iron and water. And the material with the higher specific heat will usually, let's call it win. Okay, the final temperature will be closer to that one. So the water is going to win out here. Also because of the mass. Okay, the relative mass is the water has more mass and a higher specific heat. So you'd expect the final temperature to be very close to 12, and in fact, we find it to be, I believe, about 16.4 degrees Celsius. Okay, so make sure you remember that this video exists. Use it for your own references. These are good study tools. And don't forget that the sample calculations for the solar house are due tomorrow or Saturday in class.